hello to everybody. I'm very pleased to start again this session of the AstroGeo seminar. To start with, we go over a very wide time scale because it will be over the whole age of the Earth. And but I remind you that this is one of the goals of AstroGeo, to try to have information over the whole age of the Earth. And I'm very pleased to introduce Maëlis Arnould. So Maëlis Arnould is working at the Laboratoire de Géologie de Lyon, and she works on mantle convection and plate tectonics. And recently, one of us, Mohamed Farhat, had the pleasure to hear her at a school in Les Ouches. And it was very helpful to derive a model that we needed for the continental evolution. So I think it was a good thing to invite her to make a general talk about plate tectonic on Earth and the main feature, and also to try to look to the genesis of the continents. So this is quite a wide subject, and so I thank Maëlis for challenging the task, and you can start now and share your screen. I think you can go do it.
Yes. So thank you for the introduction, and thank you, Mohamed, for the suggestion. Okay, let's go. So I tried not to take 4 billion years to talk about plate tectonics on Earth. And so I'm trying to give you some insights about some observations, the driving forces, and some temporal evolution of plate tectonics. So I wanted first to make you work a little bit. So I wanted to tell me in the chat whatever comes first to your mind when you think about plate tectonics. So I'm sorry for Mohamed, there are some slides you will see that you already saw, but yeah, for the others, I think it's good to repeat. So, so I'm going to have a look at the chat, and you can write whatever you want. Okay, so there are plumes, movements, paleolatitude, mass distribution, volcanoes, continental drift, subduction. So we have a lot of processes, some kind of, some features that arise from plate tectonics. Any other ideas? No? Okay. Chemistry, yeah. Weird dancing. Yeah, mountain building, ocean evolution. Okay. So that would be my reply, like, to this question. So for me, the Earth is an active planet, and when we look at its surface, we can see that as part of its activity, we see, for example, volcanoes, we see some earthquakes, and from all of this, we see some mountains, some topography, and from all of this, we can build what is called plate boundaries, and we'll see that plates are moving towards each other or against each other, and depending on this, we have all of this activity on the surface. And so to give you a bit summary of what I want to talk about, so we'll start from a bit of history, and then I take a look at the theory of plate tectonics and its limitations, and then what drives plate tectonics, how to reconstruct past plate motions, and then when did plate tectonics start, which is the big 4 million questions. So if we start early in the history, so before the theory of plate tectonics that we all know, I think, some people thought about why are there some mountains, why are there some continents, and why are there oceans. And one of them, which is Edward Suez, for example, thought that, okay, maybe the Earth contracted from cooling. And this idea of cooling is very important for his theory, because with this cooling, you would have a thermal contraction of the Earth, and then some cracks would appear, and some holes would be filled with water, so that would be the oceans, and the parts that would rise above water would be the continents. So, and before that, there was already some observations that were quite striking. So, for example, the correspondence in the shape of Africa and South America, the fact that tectonic deformations were confined within some areas that people would call geosynclines. And people had seen as well that when we look at the biosphere, we see that fauna and flora coexist on different continents. And so they had this idea about continental bridges to explain this. And then we have this idea of lateral motions that was already present in 1884, for example, because so as you can see on this image, you have different names with different ages and nature in mountains, and that would be explained by those lateral motions. So we had this vague idea that maybe the surface of the Earth could move or could deform, but we didn't have any clue about how to put everything together. And then we have this very important person, which is Alfred Wegener for the plate tectonic theory. So this person invented what is called the continental drift theory. So based on different clues, different observations, such as the shapes of the continents, the paleontological evidence, the fact that glaciers would be on separate, well, a same glacier would be on separate continents today, and the correspondence in rock lithologies, again, on different continents. He tried to put together all the continents. And so he made this kind of puzzle evolution, I would say, which is surprisingly still like very close to what we think was the evolution of continents at the surface of the Earth. And from this, he took like all these observations and it put everything together. And one question that he had already at that time was, okay, what's the driver for all these motions of continents towards each other in the past? Well, means that they separated from each other. They were all aggregated in the past in the Pangea continents, supercontinents. And his idea was that, okay, so that's what we knew about the Earth interior at that time. So we thought that the deep interior was called NIF, and it was called like that because it was made of nickel and iron. And then you would have this layer of CIMA for silicon and magnesium, and then Cl for the major components of continents, silicium and aluminium. And so we would think that the continents, so the Cl part, would have drifted over the CIMA thanks to two forces. And the first force was the centrifugal force, which would be linked to the Earth rotation. And so this was supposedly responsible for a drift of continents toward the equator, as shown in blue here. And then you would have the Earth rotation plus the tidal force that would cause another drift of continents, which would be towards the west. And of course, these ideas of these forces, these driving forces for the motion of the continents that Wegener discovered was played a big role into the fact that this theory didn't go through. And especially because of this person, which is Harold Jeffreys, who just fought against this theory because, yeah, actually these forces were too small to explain the actual drift of continents at the surface of the Earth. And then it took a couple of more years and more people to try to understand, okay, how continents move and what causes deformation that we observe at the surface of the Earth. And for example, some crucial observations that that led to what we call now the theory of plate tectonics. They come from, for example, Marita or Frederick Vine and Raymond Matthews, who, thanks to World War II observation of the seafloor, could understand what's below the oceans, on the ocean seafloor, and the fact that continents moved away because you have rifts, ridges and subduction zones over there. And so now the theory of plate tectonics looks like that. So here you have a map which is dates from 1968, and it's from Xavier Le Pichon, who is this person. And at that time, we started to all agree about the theory of plate tectonics. And so, according to this theory, the Earth is structured as well. The Earth's surface is structured as rigid plates that move towards each other or against each other, and well, relatively to each other. And the plate motions at the surface of a sphere, so of the Earth, can be described by what we call a Euler pole and well, a Euler axis, which is schematized here, and an angular velocity. And from those two parameters, so this axis and the angular velocity, we are able to describe any motion of any rigid plate at the surface of the Earth. And so this is what is called the Euler theorem. And this is the basis for the theory of plate tectonics. So the theory of plate tectonics is really a kinematic model, kinematic theory, which just describes the motion of rigid plates, which deform very intensively on their borders, I would say. And so here it's an updated view of this theory of plate tectonics. So you see that there are more plates now that what we drew in the 70s. And you see that, yeah, some plates are very large, some of them are very small, and you have these weird zones here. I will come back to that a bit later. So again, the plate tectonics theory today is still this theory of rigid plates that move relatively to each other and that deform only on their boundaries. And so some of the evidence for this plate tectonics theory, of course, are the topography, the volcanic activity, the earthquake activity. And from all of these observations, we can also now build plate tectonics towards the past. Well, and so these are called plate tectonic reconstructions. So here you have an example. So it started, I think, 400 million years ago. And you see here the supercontinent Pangaea, which was already discovered and drawn by Wegener in the 30s. And then hits break up here, and we'll get to the actual shape of continents today. And so, yeah, some other evidences of plate tectonics, you have the surface topography. For example, the surface topography. Here you see you have a bimodal distribution of topography with continents that are emerged in majority, where we have a sunken continent here, which is Zealandia, but otherwise they are all over the surface of the sea. And then below the sea, you have the lithosphere, the oceanic lithosphere, which lies at approximately 4 kilometers depth. And then you have the world seismicity, which is largely bound to these areas of plate boundaries, but not only, we'll see a little bit afterwards. And so all of these observations that we can now confront to Earth, to the theory of plate tectonics, they helped us to reconstruct plate tectonics towards the past. They help us to understand what we observe today, but they come with a number of limitations. And that's what we are going to talk a little bit about now. So if we look a little bit again to this map, which shows the seismicity over the world, you see that there's, for example, some areas where you have a lot of seismicity and it's not confined to a plate boundary. And if you look at, for example, the motion of individual locations here, you see that we are actually on the Tibetan plateau. Here you have the Himalaya that borders India and Eurasia. And you see that the motion of each of these points is more or less some flow of, well, is kind of flowing more than a rigid rotation at the surface of the Earth. And so this is something that we can call a diffuse boundary on continents, because so where you have mountains, you have diffuse areas of deformation. And so those deformations are not confined to infinitely infinitely small and narrow areas of deformation. They are really extended. And this plateau, this Tibetan plateau, is one of the worst example for plate tectonics, actually. And it also happens in the oceans, where a lot of the seismicity that you can see here between India and the Australian plate is not confined to a narrow area. And the origin of this seismicity is very, very unknown at the moment. Some people think that maybe it's going to break at some point and you have new plate boundaries. But so far, it's very spread. So here you see all these points are actually earthquakes location. And so this is also what we call a diffuse plate boundary. Another problem with the kinematic plate tectonics theory is that, okay, I showed you a very nice animation of plate tectonics. And there was this graph that I didn't comment at that time, which is actually showing you that all the motions of these plates that you can see here are actually bound to one plate, one single plate. They are really relative to one plate. So that's how this model especially is built. And this plate is Africa. And so Africa is here. And you can see that it moves relatively slower than many of the other plates. And so since it's more stable than the others, it's been taken as a reference for the motions of all the other plates. And you can build what we call plate circuits based on the African continent. So it means that if you have the absolute motion of Africa, then if you have all the relative motions between, for example, East Antarctica and Africa, North America and Africa, and then Iberia with North America or North European Craton to North America, you can build those plate circuits and reconstruct the whole position of continents through time. But then, so this is okay. Well, it's not easy to do first, but if you manage to do that, then you still have a problem, because Africa, I told you, we need to know its absolute motion. And the absolute plate motion of Africa is actually depending on something which is in gray here, which is a bit vague and unknown. It's written here, Indian and Atlantic moving hotspot absolute reference frame, which is related to the spin axis of the Earth. And this actually is a bit difficult to assess. So actually what we do is that we say, okay, Africa is moving relatively to hotspots, and hotspots are fixed in the mantle. And so this provides us with an absolute reference frame. And then from this, we know the absolute plate motion of Africa and then all of these other continents. So that's how this model is built. But there are some problems associated with that. So, for example, some other people have used, for example, lower mantle slab remnants in order to kind of say, okay, instead of looking at this, because we'll see a little bit later that it's a bit problematic, let's have a look at another absolute reference frame. And they look at slabs in the mantle, and they say, okay, if we take some seismic tomographic map which show the location of these cold anomalies here, which are ancient subduction zones, if we put them back to the surface, we can actually reconstruct their position. So here is, for example, the remnant of the Farallon slab, and it's actually, it would be related to this subduction zone, so these plate boundaries, 120 million years, depending on its depth now. And from that, yes?
Let me interrupt you just a minute. What is plotted in the top? What is the observable here?
Here, so it's a seismic tomographic model. So it means that, so it's actually from earthquakes, from the propagation of a seismic wave inside the Earth. You actually can recover the heterogeneities, I would say, in velocity propagation of the mantle. And so when it's blue, actually, it seems that seismic waves are going faster throughout these domains. And when it's red, it means that the seismic waves are going slower. And you can make some relationships between between the seismic velocities and the density of the mantle, of the material that's in the mantle. And so what people usually say is that when when the seismic waves are propagating more rapidly into these areas, it means that these areas are usually colder or more dense than the other bits of the mantle. And when it's the contrary, it means that the mantle is hotter. So it's written in red, and or less dense. Well, depends. It's not always true, but that's the usual way of describing things. And so these two images are actually maps at different depths of the mantle, and they show these heterogeneities of seismic wave propagation through the mantle at these different depths. So this one is 1,325 kilometers depth, and this one is closer to the core mantle boundary. And so what they say using this is that, okay, if we go deeper in the mantle, it means that what we see now there was at the surface, but earlier in time. And so from that, they can build some kind of approximated plate boundaries, saying that, okay, if things are nowadays lying at 1,325 kilometers depth, it means that they were back at the surface 120 million years ago. And if they are deeper, it means that they were at the surface much earlier ago, so 240 million years ago. And so from that, they can sort of build some absolute reference frame. So that's what those people argue. But when we look at the shape of those blue anomalies, so the slabs that are remnants of subductions, you see that today they have a lot of different shapes. So maybe they have different sinking rates. And this assumes that, well, maybe the sinking rate was the same or maybe a bit different, but the sinking was vertical, but you see that some of the slabs are getting horizontal. So it's actually quite difficult to reconstruct, well, in my point of view, to reconstruct plate tectonics, absolute plate motions from this. And even if we go back to how this model is constructed. So as I repeat, they assume here that we have mantle plumes and those mantle plumes are fixed. So here's those little red dots, for example, that can be used as an absolute reference frame for building for anchoring actually the motions of Africa and then all the other plates. Then well, if you assume that they are fixed, then you could reconstruct absolute plate motions. And some people think that it's the case, that mantle plumes are fixed. And for example, there's this paper by Trontorsvik and collaborators, which says that, okay, maybe all the plumes come from what is called the Plume generation zone, and these LLSVPs, which are dense material and hot material at the base of the Earth, they are stable through time. And so it means that, okay, mantle plumes being stable is a kind of nice assumption to make. It's not like crazy. But some other people think that it's actually not the case, that mantle plumes are moving. And for example, you have this study of Tardino, where they, by fitting the shape of the actual hotspot, the Hawaiian hotspot, and considering paleomagnetic data, they can find that actually the absolute plume motion was a southward motion, and it moved maybe more than 5 centimeters per year during some time. So, and 5 centimeters per year is quite fast. And so it means that those mantle plumes are not reliable, stable thing to build a plate reconstruction on. So that's for the mantle plumes. But then there are additional problems. And one additional problem is that actually the whole lithosphere may move compared to the mantle. And this phenomenon is called net rotation. So here you have an image showing you a kind of westward drift of the whole lithosphere as a whole on top of the mantle. And here you see many different estimates of this net rotation pole or axis here. So this is different studies showing you that it's very unclear how much it moved and how it moved actually, how it moves. And so this net rotation is something that is really difficult to estimate because we are moving with this. So it's very difficult to have something to anchor our surface and compare the surface with the mantle. It's super difficult. And then there's something else, which is the true polar wonder. So this time it's the whole mantle plus lithosphere, which moves compared to the core. And so for this, so it's also quite difficult to study. So we can use paleomagnetism to try to constrain the true polar wonder. And the basic idea is that actually because of differences in inertia inside the mantle or the surface through time. So it can be the distribution of continents or the position of LLSVPs and also the subduction zones, which are more dense, less dense bits of the Earth. Because of this, the rotation of the Earth, the inertia, the moment of inertia would make the whole mantle plus lithosphere move compared to the core. And as a result, if you look at paleomagnetic data, you would see that the north, the actual paleomagnetic north would move through time, hence the name true polar wonder. And so this needs to be removed from paleomagnetic data before the paleomag data can be used to reconstruct absolute plate motions. But the scale of this true polar wonder is really discussed. So people think that it's very small, and some other things that think that it can be very large. So it depends who you talk to, I guess. And so some people have tried to work around this problem of everything moving around and how to make an absolute plate motion, have an absolute plate reconstruction. And so here you have an example of a study here, where actually the authors have tried to optimize a plate tectonic reconstruction based on some kind of geodynamic rules that they applied. And so for these geodynamic rules, they, for example, say that, okay, the lithospheric net rotation should be less than, for example, 0.1 degree per million years for during all the time. And when they reconstruct their plates, they try to fit absolute plate motion so that the resulting net lithospheric rotation at all times stays on average below this level. But this is quite a big assumption, and no one knows actually what's the maximal net rotation that you can apply to the Earth on that. So it's a bit difficult as well. But from these kind of models with the geodynamic optimization of plate tectonic reconstructions, they can actually estimate as an output the absolute plate motions for the absolute plate motions and plume motions. And from this study, for example, they get very slow plume motions. And so they say that, okay, for the major plumes, the assumption of having like a fixed plume is an okay assumption. It's quite okay to use this. So let's go back to this plate tectonic reconstruction. So as you can see here, you have a lot of gray areas and they kind of disappear as we come back to the present. And this graph here is showing you exactly the same. It's showing you, so here on the right, the world uncertainty through age, so as we go back in time. And this uncertainty, as you can see, increases. And it increases, why? Because we have less and less data to constrain the past motion of continents and or plate tectonics. And so it's actually the problem number one, I would say, to reconstruct past plate tectonic motions. And so some of the people that reconstruct plate tectonics would tell you that earlier than 80 million years, it's really difficult to trust a plate tectonic model. And so here you have, for example, a comparison between 3 different models of tectonic reconstructions of the position of continents, and some have attempted to draw some plate boundaries 780 million years ago. So that's a long time ago. And as you can see, the continents are very differently positioned and some of them are totally on the opposite side of the Earth, really. So, so it shows you how the uncertainty grows with time. And even if we come back to more recent times, we have very different interpretations of some geological observations or paleomagnetic observations as well. So here, for example, we are about 110 million years ago, and you have two scenarios for the from the Neo-Tethys closure. So the Neo-Tethys Ocean is this ocean, which was lying between India here and Eurasia, and it closed as India went northward before colliding with Eurasia and giving us the Himalaya and the Tibet Plateau. So here you have an example of a study that tells you, okay, so times goes like that. And so it tells you that due to a mantle plumes, which is called the Morondova plume, we actually could create a range of ridges here and drift and some subductions, and these would in consequence drag the Indian plate towards the north and close the Neo-Tethys Ocean. And here you have another example with another plume involved, another mantle plume, which is the proto-Deccan plume, so the plume that lies below La Réunion now, and that would have created what is called subduction, plume-induced subductions here, and those would have eventually led to the closure of the Indian, the Neo-Tethys Ocean. So those two studies rely actually on different methods. So, for example, this study with the Morondova plume is the result of some plate boundary forces estimate, and how you can track some plates due to some forces that are applied at their boundary, and depending on the thickness of the lithosphere, etc. And here you have actually a geodynamic model, which was used to infer some kind of statistic plate tectonic behavior that was later used to build this scenario of a plume-induced subductions leading to the Neo-Tethys closure. So even close to today, when we have a lot more things that we can use in the geological record to reconstruct past plate tectonic motion, we can have different interpretations of them. So maybe one of the problems about the plate tectonic theory is that actually it's just kinematic. So as I just said in the introduction, the plate tectonic theory is really the motion of rigid plates at the surface of a sphere, and they just deform on their boundary. But what if we take into account what's below, and which is the mantle, and look for what really drives plate tectonic motions? Because in those plate reconstruction that I showed you before, actually there's no geodynamic input really, and we don't know if these scenarios of plate tectonic reconstructions are actually geodynamically plausible or not at all. So let's go to this question. So for this, we can use different methods, and some of the methods that are really used a lot are modeling. So you can actually use numerical models or some experiments in order to understand how plates moves at the surface of a mantle. And one of the first observations about the main driver of plate tectonics is actually from this figure, from this study in 1975 by Forsyth and Ueda, where they compared actually some plate motions with the percentage of the plate boundaries which were composed of slabs, of subductions. And what they found out is that as plate moves fast, the percentage of their boundaries, which was composed of subductions, would increase a lot. Hence the largest bars here. And this is called this is called slab pull. And we think that it's actually the dominant force in plate tectonics. And so later on, some other studies try to refine a little bit this kind of observations, and running some instantaneous models. This study compared, what the observed plate tectonic motions today with what would result from different scenarios. So if we just think that there's slab pull, if we just think that it's actually slab suction that dominates, so slab suction is actually the mantle that would move with the slab as it goes down and would actually attract the plates together, for example. And then if we combine both of these two forces, and what they found is that, if we combine both of the slab pull and slab suction, we get to more realistic plate velocities and more comparable plate velocities that we have on Earth today. And so, slab pull would explain still the major part of observed plate velocities today. And then, there are other forces. I won't talk you about all of them, but for example, this study used another geodynamic model. So this model is actually a bit different from the others I showed you before. So actually, the plate tectonics is a self-emergent, self-generated process of mantle convection. So it means that from this kind of model, you can study what causes plate tectonics at the surface of these kind of models. So it means that they can arise wherever they want. And this is due to a specific modeling technique, which is called the modeling tip, I would say. We use what is called the pseudoplastic rheology to model plate tectonics. And so on this model here, what you can see is the plate, the mantle velocity field here. And you can see that in the upper part of the mantle, velocities are going, maybe faster. Maybe it's probably due to the fact that the upper mantle is less viscous than the lowermost mantle. And then at the surface, you see what is red here is a ridge. What is blue here, it's a mantle. A subduction zone, and you see that they go in the earth here. And here you have the temperature field, which is colored here. And there are some numbers here. And here, for example, you have two continents that are colliding together. Here you have a back-out basin, and here you have a subduction that is growing next to a pre-existing one. And what the authors discovered with this is that actually the main driving force for plate tectonics kind of evolves a lot laterally and through time. And it really depends on the geodynamic context. So to give you a little bit more clue, so what they did is that they calculated what is called a drag coefficient. So it's called D. And it's actually a measure of the dominance of two forces. So slab pull, which means the traction of a slab and it's transferred to the plate that's attached with it. And so it drags the plate laterally. So that's what we saw earlier. And mantle drag. So mantle drag would be the contrary. It's the mantle which moves faster and drags the plates that are on top of them, on top of the mantle. And what you see on these maps here on the right is the drag coefficient. And when it's blue, it means that slab pull dominates. And when it's a little bit hot color, then it means that mantle drag dominates. And you see that through time. So here times go towards go forward towards the bottom. What you can see is that as continents move at the surface, as new plate boundaries are formed, you see very different patterns of drag coefficient in the uppermost mantle. And what we found is that actually when you have a supercontinent that's forming, you have a lot of blue here, which means that a lot of slab pull is acting on top of this supercontinent. And then when you have a stable supercontinent, then a lot of the motions of the surface are caused by mantle drag. And then when you have the breakup, it's a little bit more the slab pull that dominates again. And so this kind of informations that come from all these numerical models, for example, or analogic experiments, for example, they can be used to as an input to try to constrain a little bit more past tectonic motions. And here, for example, you see another plate tectonic model. So it's a reconstructions that starts 1 billion years ago. So it's the longest plate reconstructions that we have to date, I would say. It's very recent. And what you can see here is that, okay, so it's a lot accelerated, but you see that you still see some plates everywhere, some subduction zones, some plate boundaries, and the continents move towards each other, or they separate. And from this kind of model, we can actually recover some supercontinent cycles. So it's the same as what I just described before with the geodynamic model. So when supercontinents assemble or disaggregate. So for example, here there was one here. There's one supercontinent, and it's bringing the Pangea, and then Pangea separates. Okay, so if we look a little bit more at these supercontinents, we'll actually understand that they are quite important. So if we look at just the lithosphere, here you have drawn what is called the Wilson cycle. So the Wilson cycle would start from a stable continent, which would be this kind of raft here. And then you would have some rifting of these continents and the creation of an ocean in between two parts of the continent. And then in this Wilson cycle, the pieces of continents after some time would converge together and collide together to form a new supercontinent. And the cycle would go on, and it would take between 300 million years and 500 million years to complete this sort of cycle. So these cycles have actually some big influence on mantle convection. And so we'll see really this relationship between plate tectonics and mantle convection, for example, with the supercontinent cycle. And so here you have a study that's a geochemical study, and here you have a geodynamic model. So it's very different approaches, but they all come to the same conclusion, is that on large scale, what's inside the mantle, it really depends on the fact that you have supercontinents or disaggregated supercontinents or separated continents. And so, for example, here on this study, you have a supercontinent which is on top of this blue called Plume, and you would have what is called a degree 1 convection. So it means that below this supercontinent, which is assembling, you have subduction zones, and so downwellings. And on the other side, as a result, you would concentrate all the upwellings together, and you would have this large scale upwelling, which is a degree 1 convection, a degree 1 pattern. And as you heat the surface of, the bottom of your supercontinent, you would eventually break it. And this heat would come from the fact that actually continents are insulators, and so they don't allow the heat to escape towards the surface, or they let it, but a little bit less than oceans. And so the mantle below this supercontinent would heat, and eventually you would have more plumes coming, and this would fragment the continents, and you would see here the creation of this degree 2 pattern, which is what we still observe today. So for example, here you have another view of today with these two, what's called the LLSVPs, which are hot, maybe hot and denser areas. There's one below the Africa and one below the Pacific. And then on the other side, around them, you have a girdle of subduction, which would be represented by this thing. And this would change maybe or stay stable. This is a big debate, depending on supercontinent cycle. So in order to understand past plate tectonics and past motion or past location of continents, we need to understand, to have a look at plate tectonics, continents, and mantle convection. Those are, I think, are the three things to have a look at. And actually, if we study all of this, and if we want to make some past plate tectonic reconstruction, it's because we want to understand also what's the relationships between mantle convection, plate tectonics, and the evolution or the dynamics of the external envelopes. And this is an example from when the supercontinent Rodinia broke up, because we have some clues. So here you have some observations that we can find from the Neoproterozoic that show you that at that time, at all latitudes, which are shown by these colors, we had some glacial samples. So it means that maybe the whole Earth was covered in ice, which is called the snowball Earth. And we think that many of these events happened throughout the history of the Earth. And this one would be the last one. And one of the ideas is that, okay, to build a snowball Earth, you need very low CO2 concentration in the atmosphere. And one way to decrease the concentration of CO2 is actually to break up a continent, a supercontinent. And so here it's a simulation by Yannick, for example, where you have this supercontinent Rodinia, and here when it's broken and after its breakup. And if they account for the fact that basalts can get eroded after like these mantle plumes that can participate to the breakup, plus the fact that runoff is accelerated as well because of the breakup of the continents. They can actually absorb some CO2 from the atmosphere and store it into some rocks. And this can lead eventually to what's called the snowball Earth. So, and we think that after this snowball Earth, there's something in the biosphere that happened as well, which is some biological explosion. And we think that maybe it's actually eventually related to the supercontinent cycle, and so the geodynamic of the internal Earth. So yeah, okay, let's come back to this simulation. So I told you that it was the oldest one that we have today. And as you can see, when we start from the beginning, we still see some plate boundaries, we still see some continents and yeah, some plates that look like plates. And so the assumptions that were used to make this model were, I would say, conservative assumptions. It means that we think that the laws that we think drive plate tectonics today would be still there 1 billion years ago. But it's not necessarily the thing, it's not necessarily true if we go even further in the past. So let's have a look at when did plate tectonics start, and when, well, until when can we think that it's possible to reconstruct plate tectonics and past continent motion. So if we start to talk about earliest dynamics, there are many different ways to approach what was going on at that time. And I'm not a specialist of this period, but I try to make some points here. And I'm starting with some observations. So one basic observation is to look at, okay, where do we have some observations from ages earlier than 2 billion years, for example. And if we look at a map, here you have only the orange areas that are older, actually, than 2 billion years. And those are called cratons. And most of them are Archean in age, so it means that they are older than 2.5 billion years. Yeah, otherwise, everything is more recent. And you see that those cratons are found on continents, and the oceans, of course, they are renewed more rapidly. And so there's no evidence of very old oceans in what we have today, in the oceans today. So if we look at those cratons, we know that they are colder, they are thicker, they are usually believed as stable, more stable, and they are composed of many different rocks that we don't find today, or that modern tectonics don't really create, I would say, or mantle convection. So if we just start from this, so here it's a zircon. It dates from 4.4 billion years. It's actually some parts of this, which dates from 4.4 billion years. And those relics are actually the earliest relics that we have at the surface of the Earth from its birth. And it's really striking because when you look at those zircons, you can actually find that liquid water was stable at the surface. And the fact that we find these means that we had already some kind of continent pieces that were emerged and submitted to a very harsh weathering, maybe, This is what we can find from the study of these zircons. But if we go a little bit later, we see that there are some what is called TTGs for tonalite, trondhjemite, and granodiorite. So they look like that, for example, in the field. And those are kind of felsic rocks that we think are proto-continents. They were found a lot until the end of the Archeans, but then they completely disappear. We don't find any TTGs that are younger than the Archean. And it's the same for the comatites. So the comatites are ultramafic rocks, and they are found in green belts areas. And those comatites result from the melting of the mantle at very high degree. And so it's the same as the TTGs. After 2.5 billion years, we don't find a lot of comatites created at the surface of the Earth. So if we look at continents, okay, we have some rock compositions, we have geographic delimitation of where are the cratons, or where are the older places. And so some people have tried to build some plate reconstructions, for example, for a supercontinent that would be called Superia, 2.45 million years. And so you see that it's very, very limited, I would say, because we don't have a lot of clue actually about this. And so these reconstructions, again, assume that plate tectonics didn't change much between, 2.4, we still had like supercontinent cycle maybe, and now. And if we look back in time, actually, some people think that the answer lies in the curve of the continental growth models. So here you have different models. So it means that people don't really agree about how continents grew through time. But I would say that most of the people think that by 2.5 billion years, the volume of continents was quite the same as today, as present day. And so it means that earlier than that, maybe continents were very small. Maybe they were not existing. I don't know. And so some people have tried to understand from this what would look like, for example, mantle convection, because we saw that depending on supercontinent cycles, maybe on the continent shape, we have an influence on mantle convection. And so some people propose that, okay, if you assume that continents were very small in size, in shape, maybe you would have smaller plates and you would have this sort of smaller scale convection. And this would be helped by the fact that in the early Earth, the mantle was, of course, hotter. And that would explain, for example, the fact that we find comatites for these early times. And so if we put all of this together, some models have proposed some dynamics for the surface of our planet. Yeah. And they have proposed, for example, two scenarios. So there's the heat pipe model and, for example, the plutonic squishy lid model. So what are these models? So here you see some models with different Rayleigh numbers, and you see this graph here, which shows what's the heat pipe mechanism. So the heat pipe mechanism would be some kind of melting that would happen here, and then it would be extracted. So it's like by volcanism, and it would cool, and after that you would build some kind of proto-continents. And some of the observations that maybe could explain this very volcanic scenario, this heat pipe scenario, is the fact that we find those comatites and those green belt stones all over the Archean. And the Plutonic squishy lid is a little bit more what people think is the dynamics of other planets like Venus, and it would be the result of some delamination of the lower part of the lithosphere and the crust. And this would maybe lead eventually to more felsic composition and the birth of some TTGs. And then, some people think that, okay, if we try to compare all those end members, maybe the answer about the dynamics of the early Earth lies between them, in the middle of them. And so using those kind of numerical models, they could explore some different scenarios. So the Plutonic only, the heat pipe only. And they try to see what are the good conditions, the right conditions to make all the rocks that we have now at the surface of the Earth. And they found out that they need actually a combination of all those two different mechanisms to have the right mixture and the right temperature for creating both the TTGs and the comatites. And then, so this is a little bit, this sounds like geopoetry to me, but if you think that, okay, we had like many small part of continents that would be created by this, maybe those processes of melting, then you would grow continents. And as continent grows, it has been proposed that maybe they can trigger plate tectonics and subduction zones on their boundary by destabilizing the boundaries, the lithosphere, the oceanic lithosphere on their side as they sort of expand. So I will let you with my conclusions here. So I think that what you can take out from this is that the theory of plate tectonics is very powerful because it explains a lot of observations that we have, and it really revolutionized our understanding of some surface observations, a lot of surface observations. But in order to fully understand what we see, we really need to account for what's below the lithosphere and what's below plate tectonics. And so we need to account for the intertwining between plates, continents, and metal dynamics. And this applies today. And for me, it applies as well for the early Earth. So we need the help for modeling of geochemistry and mineralogy also to understand better what was going on at these early times. So I thank you for your attention.
So thanks a lot, Maëlis, for this very broad review. I think you really made a challenge to keep us awake, because it was a long talk, but still a new thing at each time. So it was still very interesting. And now I open for question. If so, please raise the small. Oh yes, Alexandro. Yes, you can. Yes, either raise the small hand or the big hand. We
Thank
don't hear
Can-
you.
No, can you hear me, Maëlis?
Yes, now.
Yes.
Okay. Well, first of all, thank you again, as Jacques said, for the very interesting overview. And it's nice to see some of the more recent results too, as well. I was intrigued by the comparison with the degree 2 and degree 1 patterns, which occur at different times depending on the arrangement of continents. Because, as you say, there's a debate as to what the long wavelengths in the Earth's are and how long those long wavelengths are maintained by the internal dynamics. And I think you showed a picture which compares the geochemical interpretation from Doucet, and then next to it, the Jang model. I'm trying to remember the year. I think it was 2007 or something like that.
Yes. Yeah.
Could you show us that picture again?
Yes. It's here, so I need to reshare my screen. Sorry. Up. Yes, it's this one.
Oh yes, okay. I'm trying to recall this paper.
This one?
Yes. What boundary conditions were assumed?
Yeah. So, so it was actually so the boundary conditions are not shown. You only see like some isotherms of the mantle here, but here in this case, I think he had a supercontinent here, and it was just before the breakup. Here and here it was more like okay, during the first stage of the supercontinents you still have these downwellings that go down, and before and just after that you start reheating the mantle below the supercontinents, and this would lead eventually to breakup. But these models are not like evolutionary models. It's more like an exploration of okay, what would be stable if I have a supercontinent or many different continents, and which scales would dominate in the mantle.
These models have freely moving plates, or were the velocities prescribed?
Those ones? So I think it was like instantaneous models. No, not instantaneous, but it was models where once supercontinent is in place, it doesn't move at all, and you wait until you see this pattern, and you do the same with different continents, and you wait to see what's the pattern.
Oh, I see.
Yeah. So it's two different models. It's not like an evolution.
That was my question, whether there's a natural evolution from one state at the top to the next state below, where the mantle determines the motions of the lithosphere and not the other way around. It's the lithosphere that's, because there's always this question mark. It seems, I don't know if you have some comments on this, Maëlis, but the literature seems to have quite a few geodynamic models showing the evolution of the mantle, but it looks like in many cases the velocities at the Earth's surface are prescribed rather than predicted by the models.
Yes.
Does that give meaningful results when you do that, or not?
I think it depends who you talk to. So some people. Some researchers, they think that okay, since we have no idea about the mantle in the past, we can use those kind of models, those kind of plate reconstructions to kind of push the surface, to impose that at the surface of the models, and see what would be the resulting mantle heterogeneities that you would get from this. But the thing is that if you take the same parameters of mantle convection for the mantle convection that these people have, and you let the model evolve by itself, maybe in some places you would get subductions where the model says that it's a stable lithosphere, or the contrary. And so you can get a lot of artifacts like that because you are forcing the mantle to behave as you want in some sort. So yeah, I think it's a nice approach because yeah, then you are able to really compare geographically things with what we have today. But yeah, I prefer the predictive way.
Okay. No, I thank you for that. Actually, I had a question, just a last question about this figure about uncertainty. On the right-hand side of this graphic, you have uncertainty from 0 on the bottom to 100 at the top. I guess complete uncertainty is 100%.
Yes.
And you made an important statement, I think, that if you go earlier than 80 million years, when you go into the quiet zone, it's very difficult then to connect what happened before the quiet zone with what happened afterwards. And of course, a lot of the ocean plates have disappeared at this point. They were subducted. So is this uncertainty quantified, or is this just a guessed uncertainty?
Yeah. So the authors here, I think it's in the Tetley, yes, it's in the Tetley et al. Paper, 2019. Yes. And the authors here, I think, didn't really quantify the uncertainty because, yeah, that's something I didn't say, is that any of these plate motions that we have at the surface and that we see in plate reconstructions, they have associated uncertainties for each of the observations that we have and we collected to get these plate motions. But those uncertainties, usually they are just discarded. And nobody knows how to really put these uncertainties inside those plate reconstructions.
Yeah, I think that's a good point.
Yeah. So it's actually a big problem now. And I know that for paleomagnetic data, it's when you have a measurement, you already have some uncertainties associated, but then people don't really do anything with it. And so some people try to use those data that were acquired and that are still useful in order to try to estimate what would be the uncertainty of the position of, for example, I don't know, Africa, for example. Yeah, but and there are different methods, but yeah, it depends. Yeah, it depends what you take. I know that depending on the level of the paleomag data that you take, for example, if you go on the site data or if you go on the regional data, you have different techniques for taking into account these uncertainties and averaging them. And in reality, people average everything and they don't give weights to different data that they collate on the field. And so, yeah, you end up with a kind of monster plate tectonic model that's, yeah, maybe not representative of what people really collected on the field.
Okay, thank you very much, Maëlis, and thank you again for your presentation.
Thank you.
Oh, are you done?
Yes.
Alessandro. So, Paul, you wanted to ask something. You should put your microphone first.
Good idea. The usual question, please unmute. Can you unmute your mic? I very much enjoyed that talk. I have just one relatively simple question. I'd like to know your opinion of the true polar wander event proposed for the late Jurassic by Kent and Irving and Kent et al. Because that has 30 degrees of angular momentum near the angular rotation near the armpit of Africa and North America in Pangaea, which results in China with 30 degrees latitudinal shift, both south and then back north again, which is enormous for paleoclimate. Can you comment on that?
Okay, it's not an easy question. Yeah, so I'm not a real specialist of the data for true polar wander. I'm more like a modeler, so maybe I have this modeling reply. I don't know. It seems that as we look more more deeper in any true polar wonder or large true polar wonder event that we kind of see in the paleomag data, when we look closer, it seems that when we re-estimate things, they are not that big, that large than what we believe initially. So yeah, that would be my first guess, but it's like a first guess.
So you don't feel that the magnitudes of these are as large as the proponents would argue?
I would say that it's very big.
Oh, you think it's very big?
No. I
No.
think that what they say is very big. Yeah.
Right.
Yeah.
I asked this because I work in China and north in China, and the paleoclimatic data is completely consistent with a large latitudinal shift for that time period. It goes from, what would be high latitude wet to very, very dry, and then swings back to wet again. And very hard to explain otherwise.
Yeah.
I have to deal with my plumber who's in the house just for a second. I'm sorry.
Yeah. So yeah. Maybe we go back to this question later.
We will take the question of Arno.
I know, it's okay. Yeah. So the way true polar wonder works is that you need some perturbation in the moment of inertia, and so what
polar wonder will be limited by the viscosity of the mantle.
Yes, so you would have this this dependence, plus you need to account. So that I think that's what Alessandro said. You need to account for the time scale it takes for example, an anomaly to be visible or seen in the momentum of inertia. And so that you would perturb it and then go back to something that's kind of equilibrated. So a position of a rotation that re-equilibrates or restabilize this moment of inertia. So I'm really not.
Maybe
I don't really know this.
Maybe that would be the subject of a full session.
Yes.
About true polar wonder in the past, and the observation, the model, of course, Maëlis, you are very. We are happy to hear your opinion.
So what I think is that really you need to look at where are the continents. If you have a lot of, for example, subduction flux. Because when subductions reach the lower mantle, you have like a kind of inversion of the geoid, which is used to calculate the moment of inertia of degree 2, and then you have also these LLSVPs, which we don't really know anything about, that you need to account for. And if you think that they are stable, or if they think that they move through time, this will have different effects on this true polar wonder. But I'm really not familiar with the event that you described, so I would need to look at the study, I think.
Alessandro, do you have a comment on that? No. Okay, Mohammad.
Yes, can you hear me?
Yes.
Okay, hi Maëlis. Thank you for the very nice talk the second time. So I have a couple of questions, but one of them is basically a concern with what you were just saying right now. So So I understand that the spatial stability of the plumes is generally assumed in plate modeling. And you've shown one case study, I think, about moving plumes. And I've seen very recently a paper, I think in APSL, that shows that the reconstruction of early Paleozoic subduction zones suggests that the before Pangean mantle structure was oriented fundamentally different from the post-Pangean era. And I think it concludes that across the supercontinental cycle, you can assume the persistence of the plume positions and the LSVPs, but no longer, and definitely not longer than that. So I don't know how much there's supporting literature on the behind that, and I'm personally not aware how the universal reference frame for plate tectonic models is defined. But if the plumes movement was rendered a fact, how would that affect the available models of plate tectonics? For example, the two animations that you've showed of Matthews and the Meredith.
Yeah, so so yeah, the plume motion. So to understand if plume moves or not, it's really difficult because they are in the mantle, and on top of this, we have these lithosphere motions, and so it's really difficult to try to discriminate which part of what we see at the surface is due to plate tectonics and which part is due to plume motions. So some people use numerical models in order to understand whether plume moves. So I've tried to do that, for example. And when I do that, I see that it depends. Some plumes can move very fast, especially when you have two plumes that come close to each other and they sort of merge. The merging event is really fast. It's less than 10 million years, but it's really fast. Okay. You observe very fast motions. And then you have some plumes that are very stable, that move by less than 0.5 centimeter per year. So these ones, I would consider them as stable. And some of them interact with the slabs as well. And then those can reach speeds, absolute speeds of 2 centimeters per year. So that's my point of view. It would be that it actually depends. Then you have these people that look at the geological record and say that, okay, if we assume that all the plumes are now very close to the LLSVP's boundaries, if they are anchored there, maybe they are very, very stable through time, if the LLSVPs are stable through time. But again, we don't know what are LLSVPs. So you have other people that say that LLSVPs move very fast, and so the plumes move very fast with them. So I don't have any reply for you. I'm sorry.
Okay.
Yeah, certainly I would say that earlier than pre-Pangea time, it's really difficult to make any assumption on plume position, on absolute plume behavior, and
Okay, another small question. So because one of the last points you were discussing with Alessandro, this uncertainty graph. So I guess any plate tectonics model should also certainly include the evolution of the oceanic basins through time.
Yeah.
So and Alessandro was saying that we would lose all information of basins beyond, he said something like 80 million years ago. Okay, so how, as a modeler, do you deal with the reconstruction of oceanic plates in the pre-Mesozoic?
Yeah, so so what people do for earlier times, they try to reconstruct continent positions, so continental location, and they try to see if at their borders you have some clues about maybe a subduction zone, for example, or maybe some rifting that happens at some point. And from that, you can draw lines in your empty oceanic basins, and and say, okay, here we know that the continents were here at some points and they are here at some points from different observations. So it means that they got closer to each other. So it means that there must be a subduction somewhere in between.
Okay.
Or maybe 2, or maybe 3, or maybe it's not that at all. I don't know.
Okay. Okay.
So people make some guesses. I would say it's really that you try to make a puzzle fitting all the pieces together, but you have big holes that you need to fill, and we have limited observation. So the problem is really underdetermined.
Okay.
So as a modeler, I would say that some people trust the plate reconstructions enough so that they impose plate motions at the surface of their models of mental convection. And other people think that, okay, we don't know anything. So it's better to model a plate-like behavior arising from self-sustained mental convection, but using parameters that look like the Earth, but are not
Okay.
recreating Earth's evolution.
Okay. Okay, thank you.
You're done?
Yes.
Any other question? Okay, there doesn't seem. I have one, at least, which is on the continental growth. You show the various curves of continental growth, but
I show only some of them because there are plenty more.
yeah, okay.
Yes.
But the one you show were relatively comparable.
Yes.
Okay,
Yeah.
so it doesn't reflect the uncertainty on them.
No. No, some people think that.
Can you comment on what is really known? What is solid, what is not? Is there a consensus on this continent growth? And maybe you could show back the picture, the curve you had. What is really the firm knowledge on that? And
yeah, so it was here. Yeah, some people think that it's actually a progressive, like a kind of linear curve. Some people think that already at 4 billion years or 3 billion years, we had like almost 100% of the continental crust that was already here. And I would say that these curves that really look like each other are what makes the consensus that almost all the crust was already here by the end of the Archean, so at 2.5 billion years. But well, I'm not a specialist of this time period, so I won't be able to comment more, I would say, on this, on what's before and what's after and how you get to this consensus. But yeah, so I know that already to create continents, there's not a consensus, like how you form continents from mantle or proto-mantle in the first place, and what would be their composition, and is something that's a bit debated. So some people think, for example, that actually from the melting of kind of proto-oceanic crust at that time, so which would be made of maybe serpentinite, because you would have the mantle that's directly close to the surface. If you imagine that there was already some oceans at the surface, at that time you can have like some hydrating, you can hydrate the peridotite of the mantle, make these serpentinites, and when you kind of subduct or I don't know, delaminate those pieces of serpentinite, you increase the pressure and the temperature in a certain way that can create some felsic melt. And so it's a very recent study. I don't remember the authors, And so some people think that, okay, so that's what created the continents in the first place, this process. And some other people think that actually the first continents were ultramafic continents. So they were more of a composition of what I showed here, these comatites. And then by melting, remelting, redifferentiation, you would make those, the magma evolve toward a morphic composition that we see today. But how much time did that take? I would say it depends on which scenario you really believe in. Yeah, I have no idea if there's an agreement somehow.
Okay. And when you have 10% of continent, what
Yeah.
is the remainder? What is it? Is it
Yeah.
an ocean? Is it other thing? What is beside the continent?
Yeah, so if we look at, for example, what the story of the first relics that we have on the surface of the Earth, we can say that probably water was liquid at the surface of the Earth very, very early in its history. And for example, those zircons, they show that the continental bits maybe were at the surface because they could have weathering. Yeah, and then on the other side, you would have like sort of this mantle, this proto-mantle that would have just frozen because you're next to the surface, which would be below the water, and that's the story of the serpentinite that I was telling. So some people think that it's that. Some other people think that already you have like a proto-oceanic crust or something like that. I don't know.
Okay, thanks again. And is there any additional question? Yes, Misha?
Hi there. Hi. Thank you very much for your talk. That was very interesting indeed. I do have a question. So quite a number of the people in the audience are studying sediments or sedimentary archives. And of course, sediments can be useful for many different reasons and purposes, like sedimentary provenance, telling you something about where sediments are originating from, or sedimentary geochemistry, like strontium isotope records. They can tell you something about the global extent of spreading ridges. So my question would be, like, how can we as a sedimentary geochemistry community really contribute to some of the problems that you talked about? I mean, how can we bring the different fields together, the modeling field and the sedimentary geochemistry field?
Well, one thing that I think about directly is dynamic topography, for example. So dynamic topography would be the effect of mantle convection on the surface topography. And something that's very debated today is at which scale can we see an effect of mantle convection in the topography that we have at the surface. So there are some observations, there are some models, and they all disagree with each other. And something that's really difficult to know, but I think would be interesting is like, can we see in the sedimentary record somehow the scale of dynamic topography, at which scale it can happen? So some people have already worked a little bit on that, for example, in intracontinental basins. You see the depocenter migration, and you see, you say, that's because you have a slab moving below it, and so you have this hole that moves with it at the surface. But yeah, I would say since since well, we had this beautiful story, and now it's like all questioned from new observations. So so we still need some help from people from very different fields on that. But that's not a very easy one. Otherwise, I think about sea level, because the sea level is very, well, it depends on many different things. And one thing is, yeah, tectonics, I would say. And when you make some reconstructions, you have all these curves of sea level variations, and they are all very, very different. And as a modeler, what we are interested to do sometimes is to try to know if like a sea level increase is due to this or this or this phenomenon.
Yeah,
and so we look at their scales, and and it's super difficult to understand which curve is the right one to look at, and what is the effect of, okay, the location of the continents, what is the effect of the ridge expansions, I don't know. But that's another non-easy thing to look at, I would say. Yeah.
Right, thank you.
To me, it's really impressive to be able to have those sea level curves from for example, the sedimentary record.
Yeah, no, absolutely. So some sea level curves as well as some geochemical curves that they very nicely fit some of the tectonic models, but not others, right? So they can function as a good test, but then they deviate at some time periods. And
yeah, and we don't know why.
No, exactly. So there's issues there with all of them.
Okay, and you see, we will have not the next one. The next session will be on argon calibration. It will be made by Sébastien Nomad, and the next one will be again about tectonics, but tectonics on a shorter time scale and more precise reconstruction by Alessandro Forte, who was present here. And in this case, it's really trying to reconstruct also the rotational dynamics of the Earth and the contribution of tectonics to the rotational dynamic of the Earth. So with this is also one of the components on the evolution of the spin dynamics of the Earth, which we try to recover through geological stratigraphic data. So that's one example. And also in the work we are doing on the very long time scale, we use, in fact, this global reconstruction as an input for the change in the tidal oceanic dissipation that we try to recover in the sedimentary data, like the example that Margaret has presented in a recent talk about some data, stratigraphic data at 2.4 billion years. So she had to be at the point where this continent was already existing. And you show on the map that there are not so many places where you can check for these very old sediments. So you see, Michel, it's not for no reason that I asked to Maëlis to make this talk within this series of seminars, and hopefully in the next talk you will see some effective direct contribution of this analysis to connecting everything with stratigraphic data.